Okay, good morning, bio students. I'm going to go over Activity 1.112 and show you how to do a sample calculation and give you some more background. So the chi-squared test, and this is we're just reading about how the rules of probability, the really important things to remember are the rule of independent events, which means that past events have no influence. Have to, whoa, there's a typo. Have no. To change that. The rule of multiplication, the chance that events co-occur is the product of the individual events occurring. And the rule of addition, the probability of something that can happen in multiple ways is the sum of each individual event. And we've been using those on our worksheets. Chi-square test is a statistical test that you can use to compare data collected in an experiment against a model. This is why this is important. So what we did is we flipped coins. So flipping coins is our experiment. And what we use to determine expected values were for our model would be using our Punnett square. So the model that we're testing for this one is if we're assuming that we have this cross, and we're also assuming that we can see the genotypes of the offspring, then we're looking for that 1 to 2 to 1 ratio. So depending on how many trials we do, we need to upscale that, our expectations, to get actual numbers. So in this case, if we're doing 100 flips, we would expect 25 of the big H, 50 of big H, little h, and 25 or each of the, 25 each of the little h. So as we scale that up and down for our individual results, for our different sized group results, you always want to be thinking about these ratios, and you're going to be multiplying the total times 1/4 or 0.25 to get the first two numbers, which I did for you, and then obviously by 1/2 to get the middle number. So this is our general explanation. I just went over this part. And to calculate a chi-squared value, we have this weird equation. This part is the chi-squared, and then observed. That means those are the values from your flipping, and expected are the values from your Punnett square. So we use that value twice. Then also we have this observed minus expected squared. So don't forget when you're squaring your values at the as you do your calculations. And more appropriately, you probably would want to have brackets right here, because we're going to actually do this operation multiple times. So this symbol right here, the summation sign at the beginning, means that for every possibility that we have, we need to repeat. This tells you the number of times you're going to repeat it. You need to repeat it once for each unique possibility. So in our case, we have one, we have 1, 2, 3 unique possibilities. So we're going to take the values for each of these, observed and expected, and we're going to plug them into this equation, and then at the end, we're going to add them all together. So we're going to have three partial chi-squared values. We're going to add them together, and we're going to get the total chi-squared. So I hope you're with me so far. If not, I would say you probably want to jump back and take a peek at the Mr. Anderson video that I sent you, because it'll go through this in more depth. So once we get our final chi-squared value, then the next thing we're going to do is we're going to look at a chart that tells us what the critical values are for chi-squared. Meaning, critical means that they are significant at p equals 0.05. So that's the column that we're looking for. We're also going to be looking for the number of degrees of freedom. And degrees of freedom, by definition, is the number of different outcomes you can have minus 1. And in our case, we have 3 different outcomes, as we just went over, so our degrees of freedom is going to be 2. So at this point, we've got some important values. We haven't actually calculated our chi-squared yet, but we have our chi-squared. We're going to have our p-value of 0.05, which is just standard issue when you're doing scientific studies. And then we're going to have our degrees of freedom is equal to 2. So those are the things that you need to remember as we proceed on. So what you're testing against, and we used this term before, is the null hypothesis. The null hypothesis is basically saying that null, if you accept your null hypothesis, that means that the model and data match. So this actually, for us, this means that we're right. So we're looking for accepting the null hypothesis, and I'll show you how to do that in just a second. And if we're rejecting the null hypothesis, that means that our model is not right. Our model is wrong. So in this case, if we picked simple Mendelian inheritance, that would mean that if we were looking at actual data, that it's not matching simple Mendelian inheritance, and then we have to go back and we have to revise our null hypothesis and we have to change the model. We don't do that in this case. I'm just trying to give you a clue as to how this fits in the bigger picture. Okay, so we don't have any data yet, but let's look at the chi-square distribution table, which very clearly tells us whether or not we can accept or reject the null hypothesis. So these values along the top, whoops, that doesn't exactly point where I wanted to. These values along the top right here, this is the p-value, and we decided that we were going to use p as 0.05. And then we also decided that we were going to go with 2 degrees of freedom. So then we come over here this way, and we come down, and this is the chi-squared value that we need to be under. So if we are 5.99 or higher, we're going to reject. And rejecting means that the model is wrong. So we pick the wrong thing. If we are below 5.99, we're going to accept the null hypothesis. And remember, accepting means our model is correct. So since we probably want to be right, excuse me, we want to be on this side of the line. So just remember, if we're below 5.99, we're right, and if we're above 5.99, we're wrong. And being wrong isn't bad, it just means that we don't have the right model, and we have to find the right model until we are below, and then we can say our model is correct. Alright, so for calculations for you, these are your flips. So we're using a very small data set. And for me, I flipped 32, and I just wrote these down ahead of time. I didn't memorize them, so just planning ahead to make the video go faster. 23. Expected, again, is that 1 to 2 to 1 ratio. In this case, it's a perfect world, perfect flips. I don't think anyone had perfect flips. Is going to be 25, 50, and 25. So now we're looking at doing some subtraction here. So 32 minus 25, 7. 45 minus 50 is 5, and 2. So our observed minus expected squared. So here we have 49, and here we have 25, and here we have 4. And now we have, and these are the mathematical operations up here. And now we have observed minus expected squared, which is the value in the most recent column that I filled in, divided by the expected value. So now I'm going to have to use my calculator, and I'm going to actually do that on my phone because I don't want to switch screens. So we're dividing 49 by 25. 49 divided by 25 equals 1.96. And I'd take it out to the hundredths place is probably your best bet. Now we're doing 25 divided by 50, and that's going to give me 1/2, but I'll do it anyways. 0.50. And then we have 4 divided by 25, which is going to be a really small number. 0.16. Okay, so now our chi-squared value, we simply put our addition sign right there, and we add everything up in the column. So 0.16 plus 0.5, 0.16 plus 0.5 plus 1.96 gives us a total chi-squared value of 2.62. Our degrees of freedom, again, is n minus 1, so n minus 1 here is going to equal 2. Degrees of freedom are 2. And now we go up to our chart to see if we accept or reject our null hypothesis. And my value is going to be on the left-hand side because my value is 2.62, so that puts me like over here. And 2.62 is left of the critical value, which means that we're going to accept the null hypothesis. Null means no difference. So we're going to accept, and in this case, the conclusion that we're drawing is the model and the data match. So for me as a scientist, that's a good thing. All right, so I actually did groups 1 through 10. I don't remember. I think that's what I told you to do. But I'll show you another calculation. So 1 through 10, I added them up, and I had 217 here, 457 here, and 226 right here. Expected, because we only had 600, I believe 600 total, 450, 225. So then just again, doing the math, observed minus expected. So here we have 8. Here we have a difference of 7. I don't really care because I'm squaring it next, so I don't really care if it's positive or negative. And here we have 1. So now we square that up, make it 64, 49, and 1. And that's just this operation that I did right here. I took my previous number and I squared it. And now I'm going to do some division. So 64 divided by 225 is going to give me 0.28. And we have 49 divided by 450, 0.11 rounding up. And then we have 1 divided by 225. And that is, for our purposes, that is going to be a big, tiny little 0. We add them together. We get that. That. Okay, so again, our degrees of freedom are our total number n, which is 3. So degrees of freedom equals 2. And we go back up, and we know 0.39 is way, way lower. That's way over on this end over here. So we know that that is going to be accepted. And accepted again means that our model and our data match. And I don't think we're going to get any of these here. Okay, so we're doing this a little bit different again. So this is going to be 11 through 20. Yeah, we should have one more for the end. So again, I wrote these down. For 11 through 20, we had 144, 313, 143. And this should have been 150, 300, and 150. And again, that's just following the Punnett square. This is the Punnett square model. That's what it predicted, a 1 to 2 to 1 ratio. So then we go through and do our math again. And again, since we're squaring, I mean, you can make them positive and negative if you want to now, but it doesn't matter. So this one we're going to have 36. 13 squared, that one I actually think is 169, but I'll do that one again. $169 and 49. So these numbers are a little bit bigger, which is fine. It just means that the rolling might have been a little more directional. Looks like we got quite a few quite a push away in all three of our columns there. So 36, we're going to divide that by the expected value, which is 150. And we're going to get 0.24. Clear out 169 divided by 300 equals 0.56. So even though our numbers were big, still looks like we're not even close to building up enough. 8, 9, 10, 11. So we're still at 1.13. Again, degrees of freedom, n minus 1 is 2. And I remember our critical value is 5.99. We are way, way less than that, so we're going to accept. Tells us that our model and our data match. Finally, our last calculation, 21 through 25, we found 126, 247, and 127. And if you have any intuition about how this test works and what the numbers are, you can tell that we are going to have another really, really small chi-squared value for this one. 1 over 125 equals 0.01. If we round up, then we can do 9 divided by 250. That equals 0.04. And then we have 2 divided by 125 equals 0.02. Add those up, 4560.07. Virtually no deviation from that model at all. Remember, our critical value is 5.99, and we are way less than that. So we're going to accept, and we're going to say that our model equals our data. So going through the analysis questions, I can run through these real quick too, since we're here. What did our coin flipping represent in this activity? And that represented the random chance of inheriting an H or a little h. Why are coins a good way to model inheritance? Because inheriting an allele and flipping a coin each have a 50% probability of giving you an outcome. Did you get the same chi-squared value for each of the 4 trials? No, you did not. And the explaining part, that's where I want to see what you're thinking. So I'm going to tell you, no, we didn't get the same value, but we did actually get the same result. So kind of ponder that, and you can give me an explanation for that one. All of ours accepted, and I expected that to happen, but I want to know if this is what you expected. Because what I find is that in middle school students and early high school students, when they are talking about things being the same or different, they're looking for an exact match. And what we're learning from this activity is scientists know that that is not going to be the case. We're not going to see an exact match between models and data because of the random nature of inheritance in this case. But what we're looking for is how close is it? So if you could go through and explain your ideas about that, that would be great. How can we apply this technique in a genetics study? Well, thinking about this one, and this is where it gets interesting. We just modeled simple Mendelian. But if you think about it, we also know about incomplete, codominance. We also know about sex-linked. We also know about sex-influenced. We know about multiple allele. And we know about polygenic traits. And I might have missed one in there. But I'm wondering, what would we do differently if we wanted to transition from one of these to the other? How would that change the model and our expected values? So that is what I want you to discuss and write about. I believe that is the end. That is the end. All right, so I hope this was a useful walkthrough on the calculations and interpreting your data. So I'm going to jump off here now and get this simple video. I'm not going to do anything fancy today. Get this simple video uploaded to my YouTube channel, and then I will get, right after that, I will put it into Google Classroom for you to use to evaluate your work. Thank you, and if you have any questions, please send me a message on WebEx, email, Google Classroom, whatever your favorite way to talk is, and I will help you as soon as I can.